Our next speaker is Dr. Egbert Edelbroek. He is the founder and CEO of Spaceborne United, researcher, speaker, and space tech. He's on the advisory board of Space Tech Analytics. Spaceborne United is a research and mission design company of researchers and enables the conditions for the different stages of human reproduction in space. He's passionate about accelerating space life science research, helping humanity become a multiplanetary species. His interest in space exploration accelerated shortly after he became a sperm donor in 2010 and learned all about assisted reproductive technology. This inspired him to explore options to re-engineer existing IVF technology for applications to space. He earned his PhD in courage development and organizations connecting the domains of biology, neurology, and psychology from, I don't pronounce Dutch well, Nijmegen University in the Netherlands. He enjoys innovating and exploring boundaries by connecting domains and experts that usually remain separated in order to expand the human comfort zone. So, Doctor.
Thank you, Rand, for the introduction. So, reproduction in space. Expanding the human presence obviously implies independent human settlements beyond Earth. And as Jim was already explaining really well the different challenges of such settlements, it's also clear that these settlements have to be really independent, and that requires that we also learn how to reproduce in space. That's where we come in. And what exactly do we do? So we do three things. First of all, we research the conditions for human reproduction in space. And we are building, obviously, on top of already existing research done by all the agencies and universities. The second thing is we translate those research outcomes into mission designs, including execution partners. And we translate the research outcomes into required biomedical equipment that we develop for these missions. And I can hear you thinking, that's quite big. Aren't NASA or ESA taking care of that? And that turns out to be very difficult for them. Let me explain that. So why not the big agencies? The main issue is that they are working with taxpayer money, and it's very difficult to get the support of them if you're trying to address ethically delicate matters like space life science matters, especially reproduction in space. Another problem for them is the alternating political focus. If Trump wants to go to Mars, Biden needs another focus, and vice versa. So it's really difficult for these agencies to work on those long-term goals. And taxpayers prefer to see quick results of their taxpayer money. So fortunately, these agencies, especially NASA, they explicitly encourage biotech companies like ours to address this challenge. So that's why we are positioned in a better way than the large agencies. So one thing that you need to understand is that reproduction is not just one thing. It consists of different stages. And we are focusing on the very first stage of reproduction, the conception, and also the early embryo development. And we're also looking at the very end of the reproduction stage, the childbirth, in low Earth orbit also. But today we have limited time. I will only be looking at conception and early embryo development. So we call this ARTIS. We are re-engineering IVF and make it work in space. So that's part of assisted reproductive technology, but then extended into space. So there are obvious challenges for conception, looking at mammals and obviously also human embryos, different gravity levels, radiation. There are also a lot of practical, technical dilemmas that we are working on. But mainly, we split this up in several mission approaches. We first work with animal models in a validation mission, also testing our biomedical prototypes. And then we move on to a recoverable mission where we have Earth-like gravity, 1G, and that's going to be a 5 to 6 days mission. And then we move on to adjusted gravity levels like the Moon and Mars. So how do we do this exactly? We re-engineer existing IVF technology, and we are optimizing existing technology for obviously mass and volume and energy consumption. We also add functionalities because we have to control it remotely. We also include cryogenic preservation and artificial gravity to adjust the levels. And why are we doing this? It's one step of learning how to reproduce in space. And one of the key science goals is that we have to learn what the effects of partial gravity are on embryo development. We know practically everything about the effects of normal Earth-like gravity. We know quite a lot about the effects of microgravity, but we hardly know anything about the partial gravity effects. So that's one of our key goals. So the technologies that we apply to achieve this is focusing on IVF on a chip to make it really small, and microfluidic technology. But we also add cryopreservation, as I mentioned, because the embryo development will be paused after 5 days, because it's not safe for the embryo to remain out of the natural womb for longer. So I'm not going to go into much detail, but just to give you a general idea of the life support system that we are developing. These discs, these biocassettes, as we call them, they facilitate all the biological steps necessary for conception and for embryo development. And we also monitor each individual embryo with the imaging system. So afterwards, we can see the time lapse and see which of the embryos are developing best. And these discs, subsequently, they go inside the pressurized vessel, where the climate control is also, and the right gas mixes, etc. And they go into our device with the artificial gravity, into recoverable biosatellite, which is not clear in this image, but you get the idea, and then into the rocket. And one of the options that we've been exploring very well is the Launcher 1 option from Virgin Orbit, but we are also exploring alternatives. So we also work on the mission architecture all the way from the start, all the different stages of the mission, starting from the pre-launch stages, all the way through the launch and operational stage, and then the re-entry and recovery phase, where the embryos will be recovered and examined in our IVF lab. Looking at the time, obviously it took a lot of work to get where we are, and it will take a lot of work to get where we need to go. So we have all kinds of milestones, but let's not go into too much detail right now. The same goes for all the different areas of expertise and the experts that are supporting us. One thing I want to emphasize is that these missions don't only require space technological experts and biomedical experts, but we're also dealing with a lot of ethical and legal matters. So we have experts on board for that as well. And we could not do all of this if we didn't get a lot of valuable support from the space industry, different companies. This is a sample. I don't need to go into a lot of detail here as well, I think. So let's have a look at the future of reproduction in space. There are different interesting developments that we are closely monitoring because, as I shared before, there are different stages of reproduction. And yes, our focus is on the first stage, conception and early embryo development, and the last stage, childbirth, hence our name, Spaceborne United. but we're also preparing other stages. So we are, for example, monitoring the development of artificial wombs. At the moment, actually in the Netherlands, there's a group guided by Professor Oei, who is working on a human version of the artificial womb. I think most people know this image where it's an animal version, but they are now transforming it into a human version. In this stage, for improving the lung development for premature babies who are born close to 24 weeks. But in the future, we expect this will provide interesting alternatives in case the reproductive organs might be too much compromised by radiation damage. Very interesting is also the research of Dr. Jacob Henner from the Weizmann Institute in Israel. He and his team succeeded in actually growing mice embryos outside of the natural womb for 11 days. And for mice, that's more than half of the gestation period. And this is also very interesting for us because we think this has great implications to extend the missions that we are preparing, and that we can also allow eventually human embryos to develop outside of the womb for longer than just 5 days. After 5 days, the embryos start to split in different tissues. And at this point of the technology, they need to go back into the natural womb. But if we can use the implications and the research outcomes from Jacob Henner's team, that might change. This is just a little more detail on this work. When we are talking about exploring options to enable safe expanding of human presence in space, we also have to consider the work of Christopher Mason. As he is not joining, I suggested I could share some highlights of his work. I'm not a colleague of his or anything, and I'm also not receiving a commission to promote his book. I just think it's really interesting for this topic. Christopher is exploring feasible future scenarios that enable humankind to become a spacefaring species. And I think the scenarios that he's working on are very well backed by science, so they could actually become probable scenarios. And he's focusing mainly focusing on the opportunities of re-engineering our genetics. I think the title of his book, The Next 500 Years, I understand that makes the title a little bit more exciting, but I think predicting 500 years ahead doesn't make a lot of sense. I think the next 50 years would be more interesting, and they're still spectacular. So let me share some highlights of his approach for the next 50 years. So the genetic technology is one of the key engines in biotechnology that can push humanity forward into the future years. The technological change in this area of genome sequencing in the last 10 to 15 years is really rather extreme. And making it a lot cheaper is a big part of this. So the twin studies, everybody, I think, know Mark and Scott Kelly. One went into space, the other one stayed on Earth. And this has been really valuable and helpful in learning how to do such studies in an efficient and effective way. Overall, it's the outcomes of that twin study was good news. No special red flags for example, Mars mission. Of course, there are still many challenges, but not that we cannot address eventually. So one of the next stages that we just entered in re-engineering genetics is about expanding the genome catalog And we are starting to shift from focusing on measuring to actively protecting ourselves. And for that, we need to continue to send astronauts in space and go to Mars, and also continue with the Mars sample return missions. And that will enable us to gradually start applying genome-guided medical care and genome regulation. One of those areas also include the preparing of our genes prior to sending them in a hazardous space environment. DARPA is called this their prepare project. And eventually this also helps in developing artificial human wombs. So in about 20 years, 20 to 25 years, Chris Mason expects that we can really start expanding our genetic toolbox if we can start using genes from other organisms. One of his main examples is the tumor suppressing gene, the TP53 gene, that is present a lot more in for example, elephants than in humans. And we could copy this from the elephants as one of the many organisms that we can include. And one of the things that our genes used to be able to was to synthesize amino acids, and we lost that capability, but we could reactivate those genes and reconstitute the biochemical pathways in order to increase our self-sufficiency in space. So this is also going to be the period where we can start having long-term trials on human genome engineering. So we are shifting from all the billion years of accidental evolution into guided, more designed evolution. So eventually, let me stick to the next phase of beyond 2050, where we could also, as Chris Mason predicts, start synthesizing new genomes completely from scratch. So that's where we can really start getting creative. And we could also optimize our genes for specific or even multiple environments, because that's one of the critics. If we could change our genome and get people to thrive on Mars, it could become problematic if they would return. So, but that could still be possible. If you edit the genes in a specific way, they could be suitable for both Mars and Earth, or even other areas. So let's go a little bit further into the future. After around 2150, Chris expects that we can also start thinking about life even beyond Mars, and sending our genomes to seed Earth-like exoplanets, and we're discovering them at a really rapid pace. And it takes pioneers to do all this work, and it raises obvious ethical debates. But if you look at history, all new technologies have eventually been adopted and applied, even though there were ethical discussions. We're working with IVF in space. And if you look at 40 years ago when IVF was invented, it also met a lot of ethical challenges. And it took at least 10 years before most countries started embracing this technology. And now we are extending it even into space. But when you start allowing and working with genome editing, with CRISPR technologies and such, when Pandora's box is opened, history shows that it's very difficult to close that box again. And I think Chris Mason has showed us a lot of really interesting options and benefits of those technologies. But I also agree that we need these ethical dialogues before we can do things like this. So I want to close with one of my favorite citations from Carl Sagan, because our space exploration plans I agree they are best described as a dandelion spreading the seeds of life into space, expanding the human comfort zone.
Thank you, Egbert.